Hey folks, happy Wednesday. Today I want to go over the two physical models that we're really talking about today. These two models, projectile motion and uniform circular motion, they're particularly important. They show up a lot. They're really nice first models. Projectile motion is really important because it's really a first model of things that fly. So you're going to see this model a lot. Now, don't forget, one of the keys to projectile motion is that the displacement vector, the position vector, it's a vector. We can break it down into components. The value in that is that we really have two different problems to solve. It makes the math easier. Now, the downside is that we have more stuff to keep track of and it takes more practice. But so the divide and conquer philosophy, that is breaking down into components, really relies on you getting comfortable with setting up the physics and doing the math. I actually want to do an example today. So, example 3.11, which is the dock jumping example. We have a dog who's jumping off a dock. He runs full speed off the end of the dock and jumps into the water. Now the dock is, in this case, 0.61 meters above the water. And we're told the winning dog is the one that lands the farthest from the end. So we're given an initial velocity here. It's important to note that this is in the x direction, initial velocity in the x direction. It goes straight off the dock, that is horizontal. And the question is, how far will the dog go? So we want to find the final position. So what I've done here is I've organized our variables into x and y. I'll let you pause maybe the video and take a close look at this. But I think you'll agree that these match. Now I've set my coordinate system so that x is 0 at the end of the dock and y is 0 at the water. So the way that I would go about doing this, organizing the variables as I did, is I first think a little bit about, well, what is it that I'm trying to find? Well, I remember that for constant acceleration in the x direction, which is 0 in this case, the final position is going to be the initial position plus v naught x times time plus 1/2 ax t squared, where in this case both the acceleration is 0 and we've said that my initial position in the x direction is 0 as well. That means that my final x position, the distance, is going to be v 0x times the time. So I'm going to box that baby up. But we don't know the time. The time is the time when the dog splashes down. Splashes down, which means that the height goes to 0. So now I can think a little bit about the y coordinate. So it turns out that I can think a little bit about this, but I'm also going to need the fact that for constant acceleration in the y direction, my final position is going to be my initial position in the y direction plus v0y times time plus 1/2 ay t squared. Now note that these are at the same times. The time is what connects the two expressions. I know that my initial velocity in the y direction is 0. The dog jumps horizontally. I also know that my final position in the y direction is also 0, by definition. So I have this expression. I have 0 is equal to y0 plus 1/2. I know my acceleration is minus g t squared. Okay. So if I rearrange this, what I get is, so let's work it out. I get minus y0 is equal to minus g over 2 t squared. So I do a little math here. So this implies that the time is going to be, well, it's going to be, it looks like the square root of 2y0 all over g, unless I made a mistake. I don't think I did. And so the time that we're going to find here is 0.35 seconds. So I've actually found the time. And all that's left now is to plug that back in. Now, what I could have done before is I could have counted variables. Note that at this point, when I box that equation out? Well, I know this. That's 8.5 meters per second. So I want this. Okay. So I have two unknowns here. And then when I look at this expression, I just have the same one unknown. So actually, I have two equations and two unknowns, so I know I have enough information to solve, even if I mess up the algebra. Plug that back in, and it turns out that when I do this, I think I get 3.0 meters if my math is right. Okay? So come and chat with me if that's not clear. Okay? Now, the last topic, the second topic, is uniform circular motion. One of the keys to understanding this motion is understanding the relationship between velocity and acceleration. So make sure that when you're looking at this, that it's clear that the velocity is changing. Try to, along the motion, identify the velocity, its position. What's its magnitude? Is it changing? If the velocity is changing, that means there's an acceleration. So have a clear connection in your mind between the acceleration, the velocity, and even better, the vectors themselves, the acceleration vector and the velocity vector. Now there's going to be a derivation in the book that uses similar triangles to quantify what the magnitude of the centripetal acceleration is. I don't care so much about the derivation. I do want you to know what the result is. That is, for something in uniform circular motion, so for a uniform circular motion, UCM will be a common acronym. The centripetal or radial acceleration is going to be v squared over r. So that's the speed of the object in uniform circular motion, and r is the radius. So understanding that relationship, again, if you don't memorize it, that's fine. I think you're going to be able to regurgitate it on cue, so to speak, because you're going to use it so much. This is a really important relationship because it tells us that the acceleration goes up with the speed squared, and it goes up as the radius goes down. So the tighter circle I want to turn, the more acceleration I need, and the faster I want to go, the more acceleration I need. So take a look at the example on slide 361. I think it's a pretty good one, at least as an introductory problem, but it gives you a flavor for what you're going to see. Again, as always, come and chat if there are things that are unclear, but I wish you good luck with these two topics.